Okay, so today we're going to talk about simple regression using R. And so this is going to be the first of a 5-part series. We're going to cover simple or bivariate regression today, which is just one predictor and one outcome. And then the future videos will cover multiple regression, adding categorical predictors, mean centering our predictors, and adding interaction terms, which can also be referred to as moderation. And so the way the video is going to work is we'll first go over how to run the code in R and run the analysis, and then we'll come back here to talk about how to interpret the results and how we might format our tables or write-ups if we are interested in doing so. So again, the first portion of this video will be applied and using the code, and the second portion of the video will be how to interpret the results. Okay, and so what I have here is the R script that contains the code that we're going to be going over today. And so there's going to be a portion of this code. Oh, by the way, the script that we are currently working with, as well as the data set and an explanation of the variables of the data set, are included on my GitHub page. But there's going to be an initial portion of this code that I'm going to just show you, but I'm not going to talk about because it only contains the portion that's kind of like the initial cleaning of the data set. You wouldn't need to actually do this for your data set potentially. So some of the code you see here isn't actually necessary, but I'll let you know the parts that actually pertain to just simple regression. So don't be freaked out by saying a whole bunch of stuff here that you might not necessarily need. Okay, so this data set that we're going to be working with is a data set that I originally got from another study. The link is here if you want to go look at the original study. And it is a set of data collected from employees and organizations where we are going to predict turnover intentions or employees' intentions of leaving the company from various employee level predictor variables. And so the first thing I'm going to do here is I'm going to load my packages. These are packages that you will need. You won't need them all for the simple regression video, but you'll need them eventually for the other regression videos. So I highly recommend you go ahead and install them and just go ahead and copy them into the script that you write for your code, because again, if we don't use them today, we'll definitely use them for the future analyses. So I'm going to highlight them and run them. I'm going to go ahead and read in my data set, and I'll take a look at it. And again, we have turnover, which is our outcome variable here. It's measured on a scale from 1 to 5 in this example, where 1 means that they are not intending to quit, and then 5 means that the employee is intending to quit. We have about 1,450 different observations from our employees, and we have a bunch of different variables, which today we'll only be looking at one of them. And then I'm going to run some code here. This isn't stuff that you'll need. This is just me converting my categorical variables into factors, which we won't need for today, but we'll need for future videos. So don't worry about this portion of the code. This is just something that we're doing for future. Okay, so everything starting here is what we're going to be doing today. So we're going to be predicting turnover intentions from pay satisfaction. So can we predict employees' desire to or intentions to leave their job from the level of satisfaction that they feel towards their pay? And again, both of these variables are measured on a 1 to 5 scale, where 1 means that they do not intend on leaving or they are not satisfied with their pay, and then 5 means that they do intend on leaving or they they are satisfied with their pay rather. So again, it's you can think of it as just a regular 5-point scale, where 1 means they strongly disagree with whatever the statement is, and 5 means they strongly agree, just so you understand the numbers that we're going to see. Okay, so the first thing that I like to do is I just like to take a look at the individual descriptive statistics for the variables that we're going to be interested in. The data set itself is called turnover, and then the variable of interest is also turnover, so don't let that confuse you. So to specify the specific variable that I want to see is I'm going to go and look at the descriptive statistics for the pay satisfaction. Raw just means that it's in the original measurements. You don't need to worry about that. It's just literally just a regular measure of pay satisfaction. And then I'm also going to copy this and do this again to take a look at the outcome measure, which again is their turnover intentions. So we'll run this for the pay satisfaction variable and the turnover intentions variable. And so what we see here down at the bottom is just our descriptive statistics. And it's always a good idea just to take a look at this to familiarize yourself with the data you're going to be looking at. And so here, this first one is the pay satisfaction, and we get our mean, our standard deviation, our median, and then some other things like the min, the max, the skew, the kurtosis. In particular, it's always a good idea to look at your variables to make sure that they're not overly skewed or have overly kurtotic scores, right? So we're looking to see if our skew values fall between -1 and 1, and if our kurtosis falls, generally you want it as low as possible, like close to 0 as possible, but really I would say between -3 to +3, somewhere within that range should be fine. But again, as you can see here, our skew and our kurtosis, both of those are very close to 0 for not only the pay satisfaction variable, but then also our turnover variable. So again, this isn't strictly necessary to run the regression. It's just always a good idea to take a look at your descriptive statistics before you go to do some more complicated analyses. And yeah, so we see that both of our variables appear to be just fine. Next thing that I'd like to do is I like to take a look at the correlations between the variables that we're going to be dealing with. So specifically, turnover and pay satisfaction. This is just the zero order or the bivariate correlation, and that just means that we're not accounting for any other variables. We're just running the correlation specifically between turnover and pay satisfaction. And we see down here that there is a negative correlation of 0.34. So it does look that as employees' pay satisfaction goes up, their turnover appears to go down. And we will confirm this through the regression analysis. This is just the bivariate correlation, the simple correlation. And then we can also get a plot, a heat map plot of all of our numeric variables if we want. This isn't strictly necessary either, but it's pretty cool. And what this shows us is we can look at our measure of interest, which is turnover, and we can see which variables in our data set, which numeric variables are correlated or related to turnover. So the red means that there's negative correlation, blue means that there's positive correlation, and the darker the color, the stronger the measure. And so here in the turnover column, these are the correlations of turnover with all of the other variables, and we are looking for pay satisfaction raw. And again, we already saw that this was negative 0.34. So this is just a cool plot to get like an initial understanding of what's going on with your data. Okay, so again, so far we haven't done anything with the actual regression yet, but I promise it's coming. And the last thing we might want to do when we are only interested in two variables is we might want to make a scatter plot. And so what I'm going to do is I'm going to use ggplot to make a plot from the turnover data set. This is where you specify your data set. And then this is where you put your x variable, which for us is pay satisfaction, and then your y variable, which is the turnover intentions. So again, this first turnover, that's where you specify the name of your data set, and then the second one, this is the actual y variable. It's just confusing for us because I did something stupid and named my data set the same name as one of the actual variables. So just if you do this yourself, this is where you put your data, this is where you put your x variable, this is where you put your y variable. So we'll go ahead and run this. Oh, okay, when you get this error, this means that you have too much going on with your graphics, so you need to clear your plot. So come over here where my cursor is and press this little broom that says clear all plots. And so now we'll rerun this, and sure enough, here we go. Now this doesn't look all that meaningful, just the scatter plot by itself. So let's go ahead and add the regression line. And so I'm going to come down here, and I'm just going to do this, and I'm going to add a title to it. And then here we have our plot with the regression line. So we can see here's that negative trend that we thought existed. And I just like to do this before running the regression analysis. Again, not strictly necessary, but it gives us a nice insight into our data. So now finally, we'll create our regression model. So this is how we do it. We're going to say M1, that's the name of the regression model. You can call it anything, but I just like to keep it simple. So M1 for model 1. And then we're going to run LM for linear model, and then turnover, which is our y variable, tilde, which means predicted from, and then our x variable. So turnover, predicted from, pay satisfaction, and then we say the name of our data set. So we'll go ahead and run this code, and now up in the top right we see where M1, model 1, is now saved as a LM, or a linear model. So now it's time to go ahead and look at our results. So to get your results, you run summary M1, which again is the name of your model, and let's take a look at what we have. So again, I'm going to go over how to interpret these results in the second portion of this video, still in the same video, just towards the second half. So I will explain how to interpret these later. I'm just going to show you where to get the information right now. So here we see a review of what we input for our model, which was turnover predicted for pay satisfaction. And then here's what we really care about, the coefficients. So this right here, this first line, this is the intercept. The estimate is the intercept coefficient. The pay satisfaction, which is our predictor, the estimate for that is the slope for the pay satisfaction variable. So again, our intercept estimate, our slope estimate. Here's their standard errors. Here's their t-statistics for the hypothesis test of whether or not these predictors, the slopes of these predictors, is significantly different from zero. So again, it's a hypothesis test that these predictors are significant predictors of our outcome of interest. And as we can see here, this is the p-value, and we see that the p-value is tiny, so it's definitely significant, right? Pay satisfaction is a significant predictor of turnover intentions. And then finally down at the bottom we have our R-squared, so it looks like about 12% of the variation in turnover intentions can be predicted from our model, which again just includes pay satisfaction. So we could also say 12% of the variation in pay satisfaction, 12% of the variation in turnover intentions can be predicted from pay satisfaction. Here's the adjusted R-squared, and then here is our F-statistic, which don't necessarily need for simple regression, but we'll need this for multiple regression. Okay, so this was our model summary. And so again, that was summary M1. And so now let's get a confidence interval for the unstandardized slopes, or the unstandardized raw regression coefficients. Because everything that we see in the summary that we just looked at is the unstandardized slope. So now let's get a confidence interval again for the unstandardized slope. And here's our confidence interval for the raw slope of pay satisfaction. It falls between -0.47 and -0.35. We'll run this effect size to get the standardized regression coefficients, or the beta weights. And here it is, our coefficient, our standardized coefficient, our standardized slope, our beta weight for pay satisfaction as a predictor of turnover intentions is -0.34. And here's the confidence interval for that standardized slope. And then lastly, we might want to get a confidence interval on the R-squared value. And so what you have to do is you have to input the R-squared value that you got from your model summary, which again was here, and then you input your degrees of freedom for the F-statistic. And the F-statistic has two separate degrees of freedom, one for the model and one for the error, and that's right here in our model output. So we see the first one is 1, and the second one is 452. So the model degrees of freedom is 1, the error degrees of freedom is 1452. So you put this in, and then we get a confidence interval for R-squared. Here's the lower bound, 0.086, and the upper bound, 0.148. We can also run this to get a prettier looking version of the model output if we want. So you would just need to change this to from M1 to whatever you name your model as. We'll go ahead and run that. And sure enough, we see right here, sorry, you can't see on your screen. There we go. This is what it does. It gives us a slightly prettier version of the model summary that R gives us. And so here is the intercept estimate, here is the slope estimate, and then here is the standard error, and again, this is the unstandardized estimates. Okay? And so now we'll go ahead and look at our regression diagnostics to check our assumptions. So remember, we assume that at the population level, our errors of our regression model are distributed normally around a mean of 0 and that they have a constant error variance. This assumption is required for the significance tests where we test the significance of the regression slopes. If our assumptions are not met, we can still get the same slope estimates, but our standard errors will be biased, which means that our hypothesis test and our significance test of those estimates may be different. So again, if we're checking to see if we have met our assumptions, and these assumptions are required specifically for the model, but they won't necessarily impact our estimates of our coefficients. They'll impact the standard error estimates and the resulting significance test. But you always want to check your regression diagnostics. This will be especially important when we talk about multiple regression. And again, I'm just going to show you how to get them right now. I'll interpret them in the second portion in just a minute. So there's two ways you can do this. You can do this with what we call base R. You can run plot, and then you put the name of your model, so plot M1. And then down here at the bottom, you have to put your cursor in the console and then hit enter, and it will give you multiple different diagnostic plots. So you just keep hitting enter until it's done. A fancier way of getting these same plots is to use these functions here, and these are from one of the packages we installed above, and all you need to do is type in these functions and then again put the name of your model, which for us is M1. And it's just a prettier version of what the base R will give you. So you can just use the regular stuff that we just looked at. But if you want the prettier ones, and again, I'll go over all these in a minute. And so now we have finished running the code for our regression model, our simple regression model. So now we're going to go back and we're going to take a look at how to interpret these results, and we're going to look at what things we might want to report. Okay, so we're back at our PowerPoint. Okay, so here we go. So what we see here is the information that we got from our model summary and the other stuff that we ran. So I'll go over it step by step. And the easiest way for me personally to display the output of a regression model is to make a table with all the information. Instead of trying to type out everything by hand, just make a table. So what we have here, what we have here is the variable, or the predictor variable. So we have our intercept and our predictor variable, which was pay satisfaction. And then this right here, this B, this is our unstandardized slope. And then we have our beta weight, which is our standardized slope, and then our p-value for the significance test of these slopes. Okay, and then we have a 95% confidence interval for just the standardized regression slope. I could have also put in a 95% confidence interval for the unstandardized regression slope, which is this B right here, but personal preference, I usually report the 95% confidence interval for the standardized slope. But it's always good to also report just the raw point estimate as well. So one more time, we have our raw or unstandardized slopes, we have our standardized slopes or beta weights, we have our p-value from the significance test. I left the intercept blank because that's really unimportant in terms of whether or not it's significant. And then we have the 95% confidence interval for our standardized regression coefficients. And then we also have our model R squared. Once we talk about multiple regression with multiple predictors, we'll have a couple of other things, but this is all we really need for the simple regression. And then this is just the scatter plot with the regression line from what we saw earlier. And so again, I got all of this information from the code that we ran earlier. There's nothing here that's new that we didn't already look at. So how do we interpret this? Well, let's go over it. So this is the same table that we saw in the previous slide. And then the first thing we'll talk about is the intercept. So the intercept tells us, it's this first bullet point, it says the predicted level of turnover intentions for individuals with 0 pay satisfaction is 3.51. Now remember, in this instance our variables are measured on a scale of 1 to 5. So this intercept isn't necessarily meaningful from an interpretation standpoint for us, right? No one has a pay satisfaction of 0 because it was measured from 1 to 5. But the intercept is always interpreted in terms of it's your predicted Y when your X variable or variables are all equal to 0. So that's just the interpretation of the intercept. We'll talk about some tricks we can use later to make the intercept actually have something that's useful or meaningful, but in any case, it's literally just the predicted level of turnover intentions, which is your Y or your outcome measure for individuals with zero pay satisfaction, which is, again, our X variable. So the intercept predicted Y when X is equal to 0. In terms of the slope, for every 1 unit increase in pay satisfaction, turnover intentions are predicted to decrease by 0.41 units, right? And it's decreasing because it's a negative slope. And this makes sense intuitively. As you increase in your pay satisfaction, you're less likely to want to leave your job. And then for the interpretation of the standardized slope, for every 1 standard deviation increase in pay satisfaction, turnover intentions are predicted to decrease by 0.34 standard deviations. Again, that's this right here. That's our standardized regression slope. So that interpretation is that for every 1 standard deviation increase in pay satisfaction, turnover intentions are predicted to decrease by 0.34 standard deviations. And then finally, for our model R-squared, roughly 11.6% of the variation in turnover intentions is explained by our regression model, which in this instance is just one variable. It's just pay satisfaction. And then finally, if we want to make a fancy APA-style write-up, one thing we could do is we could say a linear regression analysis indicated that the pay satisfaction was a significant negative predictor of turnover intentions, and then I give the slope estimate, which in this case was the unstandardized slope. I give the t statistic, which was negative 13.81, which I got from the model summary, and then this is the degrees of freedom for our model. Because it's a t statistic, we only have the one estimate of the degrees of freedom, right? When we talk about the F statistic later, that's when you have 2 different degrees of freedom to report. But again, it just says a linear regression analysis indicated that the pay satisfaction was a significant negative predictor of turnover intentions, and then the slope, the t statistic, and then the p-value. And then another way we can say this, and this is in terms of the F statistic that I mentioned, we can say the one predictor model, including pay satisfaction, was able to account for 11.6% of the variance in turnover intentions. And then we report our F statistic, which again was in the model summary output, and then our degrees of freedom, and we have 2 of them because it's the F statistic. Then followed by the actual R-squared value, and then the 95% confidence interval for R-squared. And so this is in APA format. It's just a more formal way of writing what we already have in the table. Me personally, I prefer to just refer to tables, but I know that some people prefer to write it formally in this type of style. And then finally, we have our regression diagnostics. And so I talked about this earlier. Now I'll actually explain what we're looking at. So these are all the slightly fancier versions of the plots that I showed you how to get in the diagnostics section of the code. So the first thing we'll look at is this histogram of the residuals. And so it's kind of hard to tell. I'm sorry, it's kind of blurry. But this right here, this is 0. And what this is showing us is that we want our residuals to be normally distributed around a mean of 0, because that's our assumption is that the errors in the population are distributed normally around a mean of 0. And then another assumption too that we'll talk about in just a second. But as we can see here, it does look like our residuals are distributed relatively normally around a mean of 0. We can also tell this from the QQ plot here. If the residuals are distributed perfectly normally around a mean of 0, then all of these blue dots, the residuals, would fall perfectly on this red diagonal line. So that would indicate that they're perfectly normally distributed. You're never going to have it be perfect in real life, or very rarely, I should say. And so we can see that they don't appear to be perfectly normally distributed because they're starting to fall away from this red line here once we get in towards the more extreme ends. But for the most part, it's not awful, right? It still appears that our residuals are distributed relatively normally around a mean of 0. Now, slightly more problematic is our assumption that the variance, the error variance, is constant across all of our fitted values, or across as we proceed along X, right? So again, this is the assumption of homoscedasticity, or the assumption of constant error variance. And so what we're looking for, that's this plot here, is ideally we would want these blue dots, these residuals, to all be spread out equally as we proceed from left to right. On the bottom axis is the fitted value or the predicted value, and so what we would want to see is that regardless of the fitted value, our residuals would be spread out roughly consistently, which would indicate that they have constant error variance. We also want to see that the red line would fall kind of like halfway through the middle of these spreads of residuals as we see kind of over towards this end, right? This is more of what we want to see. And again, we want the spread to be consistent as well. But as we see in our example, for the predicted values or the fitted values that are lower, it looks like our model isn't predicting as well, right? We don't appear to have this constant error variance across all of our different fitted values. And we can kind of see that down here. This is the scatter plot of our actual data, pace satisfaction on the bottom, the x-axis, turnover intentions on the top. We can see that as we get towards the lower predicted values of turnover intentions, right? Because remember, turnover is on the y-axis, so this is the lower fitted values or the lower predicted values of turnover intentions. Look at this right here, okay? These are the actual observations, and what we're seeing is that our model doesn't appear to be predicting all that well. Now, part of this is due to the fact that our data can only range from 1 to 5, right? So once we get down to these lower predicted values, it's going to be pretty impossible for us to have residuals that are, going to be below the predicted value, right? And that's why it looks like most of our errors are in terms of us underpredicting, right? The actual observations are tending to fall above our predicted value, which is the regression line. So again, this is showing us that when we're looking at our lower predicted values, our lower fitted values, our model isn't performing as well. It's tending to underpredict. Determining whether or not the assumptions are violated is a little bit of a subjective effort, right? This is one of those examples where it's not great, but there's no clear right or wrong answer in a situation like this, right? There's some situations where if your assumptions are clearly not met, then it's pretty clear that you need to look at something else, right? But in this instance, this is kind of borderline, and I would say that we are probably fine to interpret our regression results in our significance tests of our slopes. So this is how you look at these residual diagnostics to get some information about whether your model assumptions are met. And so that takes us to the end of the simple regression video. The next video we'll talk about multiple regression. And again, as always, the code should be posted to the GitHub link, and the GitHub link should be in either the description for this video or definitely on the About section for my YouTube channel. Thanks for watching, and if you have any questions, feel free to leave them in the comments, and I will help you out. Thanks.